This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome. So today's lecture is worked examples. We're going to go through the compression ignition and spark ignition engine, so the Otto cycle and the diesel cycle, and then what's referred to as a mixed cycle. Just to play around with the ideas. So, Otto, diesel and mixed. As a refresher, the Otto cycle is the spark ignition cycle. This is the one where the working part of the cycle is the compression. I'll wave my mouse around. The compression, heat addition, expansion, and then exhaust. We idealize these processes as an adiabatic isentropic compression, an isentropic adiabatic expansion, and then a constant volume heat addition and a constant volume heat rejection. So those are the tools and the rules that we use to move our way around. The Otto cycle and the diesel cycle we use ideal gas for. So usually to solve these problems we're using the PV equals RT, and we're using any other rules that we've developed for ideal gases, like the temperature ratio connecting to the volume ratio for an isentropic compression. The terms that we introduced were bottom dead center and top dead center, in terms of if my cylinder is operating up and down, when the cylinder is all the way down, it has its maximum volume, and that's referred to as bottom dead center. You can see the maximum volume, this is P versus V, so the maximum volume happens over here, bottom dead center, BDC. And as it compresses, it goes to top dead center, its minimum volume, which is not zero volume because there's still a little gap between the piston and the top of the engine. And so at top dead center, there's a little volume, and you've compressed to a higher pressure. So just to remind you of the cycle and what the terminology is. The question that we'll work through for the Otto cycle says we have a compression ratio of 7. That compression ratio is the ratio of the biggest volume to the smallest volume. So I'll jump back one. I can see some frowns. When we were playing around with derivations of thermal efficiency, for example, we wanted to find an analytic expression for the thermal efficiency that was delivered in terms of a property of the working fluid and the physical geometry of the ideal engine, without knowing anything else about the engine. How many cylinders, how fast it's operating. This is 4-1 cycle. And we had this term RV, which is the ratio of this big volume to the little volume. That defines the Otto cycle. The thing that happens in the Otto cycle is go from big to small, and then small to big. The geometric change, the PDV change, is from a big volume to a small volume, then a small volume to a big volume. We have tools for isenchoric, so constant volume processes with PV equals RT. So we have all the tools we need to solve this problem. Compression ratio of 7 at the beginning of the compression process, which is to say at the start of the cycle, I've got 90 kilopascals, 27 degrees Celsius, and a volume of some cubic meters. And the maximum cycle temperature is 1127 degrees Celsius. 27's in there because it turns nicely into a round number when I turn it into Kelvin. Maximum cycle temperature happens after the combustion, happens after the heat addition. For each repetition of the cycle, calculate the heat rejection and the network production. Also calculate thermal efficiency and mean effective pressure. Use constant specific heats at room temperature. So there's some code words. Constant specific heat means that I can assume CP is the same no matter what I do. At room temperature means I can just use the CP and CV values at 27 degrees. These are called the cold air standard assumptions. And then the answers are given. So we'll put all of this onto our paper and start to work our way through. Blank piece of paper. First thing I do is start to transfer the information of the question to the paper. That's a big frowny face. Oh, sorry, I wasn't expecting to have that much of a visceral reaction to doing a question. Okay, so we're doing an Otto cycle, and we get our first marks by not calculating anything. We get our first marks by drawing diagrams and writing down the data. So I draw my marks. I draw my marks. Nice. I draw my diagram, PV diagram, and I start at point 1. Point 1 is the beginning of the compression. I have an isentropic compression, constant volume, heat addition, isentropic expansion, constant volume, heat rejection. 1, 2, 3, 4. To compress requires work. This is Q in. This is work out. This is Q out. If I was in an exam situation, bring a ruler so you can draw straight lines. So I've scribbled a straight line there. I would like that to be as straight as I can because I know it should be straight up and down on the V line. Given some values. Given P1 equals 90 kilopascals. T1 equals 27 degrees C equals 300 Kelvin. V1, big volume, equals 0.004 cubic meters. If I take a look at this data set, I've got loads of information to pin down the state for point 1. In fact, I've got more than enough information. Just here, I've got enough information to pin down the state. I've got T max, which on this diagram is the end of the combustion process, the end of the heat addition, which is 3. T max equals T3 equals 1127 degrees Celsius equals 1400 Kelvin. And I've got that RV equals 7. Find, am I still on the screen? Find heat out, network, thermal efficiency, and I'll just put a little reminder note, 1 minus 1 on RV, gamma minus 1, which is to say I could solve for part C without doing anything else because I've got RV and I've got gamma. When I say I've got gamma, what I mean is I was told to use air, and either the question would specify the gamma in the question, or you'd look up a table for what's the gamma of air. Okay? And D, what's the mean effective pressure? I'm just going to make a little note here. The mean effective pressure is if I were to do all of that net work over that change in volume and just have it as a straight line on my PV diagram. So the concept here is for the network that I've got over that volume, that could be represented as a straight line. Area under the graph is work on a PV. So I'm going to draw a big bracket around this. So this is what is the pressure that volume change would have given me the same work. It's a way of describing engines. So we'll come back to this guy when it's time to calculate it. Am I still on the screen? Yep. Assuming cold air standard assumptions. With air, gamma equals 1.4. You would look that up or you were given it. We also can then take any other property for air. So CV for air, 0.718. If you wanted it, CP for air equals 1.005, R for air equals 0.287. So we've actually got quite a bit of data, and we also know that PV equals RT, or PV equals MRT. You notice up here we were given a full volume, as well as enough information to work out P and T. So just in the back of our minds, we could be thinking, if I need to, I could determine the mass of this system. So there is the question, with all the stuff laid out, assumptions, given data, a nice diagram, the goals of the exercise, and we put that up right up on the front so that I know which direction I'm going when I start to solve the problem. Which is to say, I don't see the problem and start randomly answering bits of it. So I don't see the problem and go, I've got RV, that means I can quickly solve part C without solving any of the other stuff. A nice structured way makes sure that if there's any errors, they're easy to spot, and it also reduces the chance of errors, like throwing your pen on the ground. Okay. So, usually what we do with these problems is, as a first point, we try to work our way around each of these and make sure that we've got at least two independent intensive properties at each location. We're doing that so that I've got the state at each point. Once I can pin down each point, the rest of the analyses, the delta U's, the delta CP's, the Q's, the W's, all of those fall out from those data. So the first place to begin is working your way around the cycle. Let's put the arrows in there so we know which way we're going. As I scroll up, I'm just going to keep the cycle drawn in the corner as a reminder. One, two, three, four. And that'll just keep us on track as we're going through. So, a couple of things. I'm going to start with a mass, 90 kilopascals. This is a reordering of this guy. Mass equals PV on RT. So, times 0.004 over 0.287 times 300. Kelvin, 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 Kelvin. If you're ever in doubt, try substituting 0 in and see whether or not the equation would break. 0.00418 kilograms. Why would I solve for mass first? Why wouldn't I try to work my way around the cycle? Actually, it doesn't matter too much yet. If I started off working my way around the cycle and solve for mass later, that's okay. So at the moment, this is just an arbitrary call on my part that says it's asked for total heat transfer, it's asked for net work. I'm probably going to need the mass at some point. How about I do it while it's in my mind? Okay, now we'll work through the cycle. We're going to go process 1 to 2. 1 to 2 is here. This is my isentropic compression. Ideal gas isentropic compression, we're going to use T2 on T1 is equal to V1 on V2 gamma minus 1, which will give us that T2 equals T1. Now, V1 on V2 is my compression ratio, which is my RV, which was 7 for this problem. RV. Gamma minus 1, gamma was 1.4, so 1.4 minus 1, so this becomes 0.4. So 300 times 7 to the 0.4 equals 653 Kelvin. That's a good beginning. That's given me T2. And I had volume at 1, I could get volume at 2, I could get specific volume at 2. I've got lots of things that I could determine at 2. The reason why I'm not chasing after any extra stuff is on an ideal gas process, a lot of the energy transfers that I want to calculate can be solved with delta T. Internal energy can be solved with CV delta T, enthalpy can be solved with Cp delta T. So for the moment, just finding the temperatures at each corner will be enough for me to solve energy transfer problems. On an adiabatic process, where I've got no heat transfer, I've just got work equals delta U. Yeah? So, if that's given me, I've got this guy, and I've just worked out temperature here, then the next one, I've been given the temperature here, so the next guy I'm after is here. So let's go process 3 to 4. What I'm going to get is T4 on T3 equals V3 on V4, gamma minus 1, so that's all upside down. V3 on V4 is the inverse of my compression ratio. So I'm going to get T4 equals T3 times 1 on RV to the gamma minus 1, 1400 times 1 on 7 to 0.4 gives me 643 Kelvin. So now I've got the temperature at 4. So all I did there was use my equation for an isentropic compression or expansion, or an isentropic process, to determine the temperature after the process. I've got geometric information about the engine, and I use the ideal gas, cold assumption, isentropic process to get to the next point of that. That's finished mapping, so now I look back at what I'm trying to solve for and try to decide whether or not I can solve for it. So I'm going to come back up here. I'm after Q out, work net, efficiency. Let's work on these two guys. So A, Q out equals mCV T4 minus T1. Q out was here, constant volume process. Work done in this process is what? What's the area under the PV graph for that process? I heard one whisper in the back. Oh, 0. So, straight up and down lines, we choose the graphs that make our life the easiest. This process is mapped on a PV diagram because it's nice to know when work equals 0. Process 4 to 1 has work equals 0, so the only thing in this equation is CV delta T times mass, and I can plug all that in, 0.00418 times 0.718 times 643 minus 300 equals 1.09029 kilojoules. And that's part A done. B gives me work net. I could try to calculate work out and work in, and do work out minus work in. But if I've just calculated heat out, net work is the same as, on a cycle, net work is the same as net heat transfer. So because I've already done one piece of the work, why not keep my job simple and say that this is Q in minus Q out, or Q net? Because I've already got this guy, and so I'm only now needing to solve one more thing. Just making my life as easy as I can, which is to say, if I do mCV T3 minus T2 minus 1.029 kilojoules and plug all that in, I'm going to get 2.241 minus 1.029, going to get equals 1.212 kilojoules. For C, now that I've got network and heat out and heat in, I could use those numbers, or I can use the formula. Both are perfectly legitimate for me to solve this. So for This guy, we could try with 1 minus 1 on RV to the gamma minus 1, and we're going to get 54.1%, which is the answer. And on D, remember that RV was 7, so this is 1 on 7 to the gamma minus 1. Gamma is 1.4, so 1 on 7 to the 0.4. D was asking for the MEP, which is equal to network over delta V. So I've got 1.212 as the network over V max minus V min. And V min we have not yet calculated. So V max we've got. This is going to be 1.212 over V max was 0.004 minus, what's the smallest? The smallest volume I've got is 1/7 of that. That's the point of the compression ratio. Compression ratio of 7 means the smallest volume I could get is the biggest volume divided by 7. If I put all that in, I'm going to get 353.5 kilopascals. So that's including me introducing the topic. That's all taken 25 minutes. The actual working, including lots of conversation, is taken about 10 minutes. And that's a full analysis of a thermodynamic cycle, determining temperatures all the way around, and then determining the efficiency, the work output, the heat transfer at different points. Now, obviously, I know what I'm doing. At least most of the time I know what I'm doing. Which is to say that after enough practice, this stuff starts to come quickly. At the beginning, when you're reaching for formula and you're reaching for solution methods, they don't come quickly. And so part of the objective between now and Friday is immersing yourself in how would I choose which questions, how would I choose which equations when? Do I have the confidence to use those equations? Do I know what a CV and a CP look like and when I would choose CV and CP? Do I know when I can use delta T, CV delta T or CP delta T and not? Do I know how to do an isentropic expansion or compression? Do I know how to use PV equals RT? Do I know how to use tables to solve these problems if I'm using tables? So those are the ideas that you're trying to make sure that you've exposed yourself to and tested yourself on and are deciding whether or not you can do them. As the tutor, as Antonio announced this afternoon on LMS, we are available to help you if you get stuck on working. So as you're going through this stuff, if you get stuck, send one of us, Jacob, Antonio, or myself, a photo of your working. The tutor's emails are on the LMS in the subject information flyer. There's a PDF of subject information. Second line, third line is both tutors' emails. If you're doing this stuff and you get stuck, and you're not quite sure why it's breaking, send us a little photo of your working, and preferably the problem so we know which problem it is. Often we can solve your problem very quickly because we've seen most of the ways these things can break. It might be as simple as, you're supposed to use tables, or you use CV instead of CP, stuff like that. If you're really, really stuck, then we can sit down for 5-10 minutes and chew through the problem. Yep.
What if you have no clue of the question?
Sorry?
If you look at the question and you have no clue as to how to go about the answer?
Then it's even more important that you talk to us.
Yeah.
Like this is the time to be really, really focused and saying, if you're at the point, you know it. You know when you look at a thing and you're like, that's a really good time to talk to us because we can help you start to map the thought process on a blank page. So the thought process on a blank page begins, one of the reasons why I give you that early map of draw a diagram, write the goal down, write the stuff down, it's partly to get you writing. So it's partly to make sure the first thing you do is so automatic, you know that you can fill a third of a page. And it's not about filling pages, but you know that you can be writing before answering a question. And that you'll find that the process of scribbling this stuff down starts to connect things and starts to connect ideas. You're like, I'm sure I've drawn this diagram before. I know I've traveled a curve before. I can do this. But if you're looking at a question, you're like, I don't even know where to begin, please get in touch. All right, we'll jump back Were there any questions on that Otto cycle? Like, did any of the stuff that just happened? No? Okay. So, what we're going to do now is the counterpoint. Reciprocating engines, closed volumes, CV delta T, CV delta T, CV delta T, except for the heat addition in a diesel process. That's the catch. The thing we learned as we were studying diesel process is that because the heat addition in a diesel process has a change in volume, we solve that one with enthalpy, not with internal energy, which means we solve it with Cp delta T, not Cv delta T. We'll do that in the work example. I just want to refresh that idea. So it's still the same. I have a piston that's going from biggest it can be to smallest it can be, and then back to biggest it can be. So I still go from 1 to 2, that's my isentropic compression, but in this problem, I expand a little bit while the heat's coming in, and then I have an isentropic expansion from 3 to 4. So we've got tools for this. We can do this. What I've got now is a diesel cycle. Pressure and temperature at the start of compression, so 0.1, 40 degrees, 101.3 kilonewtons per square metre, which is to say 1 atmosphere. A compression ratio of 13.1 and a cutoff ratio of 2.1. Just as a reminder, the cutoff ratio. We come back to this graph. Compression ratio from here to here. Cutoff ratio is the volume ratio from here to here. Expansion ratio is the ratio from here to here. So compression, cutoff, expansion. We're using air as the working fluid, sketch PV and TS diagrams for the cycle, and then determine maximum cycle temperature and the cycle thermal efficiency. So maximum cycle temperature is 2 and 3. No, that's not right. Maximum cycle temperature is after the combustion. Excuse me. So we're after the temperature at 3. We're going 1, 2, 3, 4. We're going to work our way around with the tools we've got. And if we got stuck, we'll have a bit of a think about how to keep moving. So we start in the same place. I don't know what I'm doing yet. So I've got a blank piece of paper and a pen. And all I've got to begin with is the tips and tricks that I've learned in thermo class. And the most important one of those is start writing down the problem. Diesel cycle, given. Leave myself plenty of space to draw some diagrams because they actually asked me to, which means if they ask me specifically to do something, there's probably marks for them. So given that P1 equals 101.3 kilopascals, T1 equals 40 degrees C equals 313 Kelvin, RV equals 13, RC equals 2. Find T max equals T3 and thermal efficiency, which we can do as net work over Q in, or if you've memorized it, all right. Given how long it is to write this down, if you haven't memorized it, by the time you've determined your way around the cycle and found the temperatures of each of the corners, it may be easier to do this guy. It depends on how your question evolves as you start to work it out. So at the moment, we're not sure which one's going to be easier, although if I've memorized this, I've got this and I've got this and I've got this and I've got this, I could probably just sort this out. Now, it asked me for some graphs. It asked me for a PV diagram. That's okay. I know how to draw a PV diagram. We'll do the TS diagram as well. P, V, T, S. Good. Good, good, good. I've got axes with labels on them. Which means that whatever happens next, I will have drawn a PV diagram and AETS diagram, provided that I draw some scribbles inside the axes. Whether or not it's absolutely the correct one or not, the fact that I've drawn my axes and labelled them has actually got me somewhere. I'm not kidding. I'm really not kidding. So we get an isentropic compression, constant pressure, isentropic. This is Q out. This is Q in. Let's give some numbers. 1, 2. This is work in, work out. 3, 4. And over on the TS diagram, I've got an isentropic compression. 1, 2. Isentropic on the TS diagram, straight up and down. So on the PV diagrams, if you don't get the P processes and the V processes right, you've got a serious problem. So if you know there's a constant volume process and it's not a straight up and down stick on your PV diagram, something's going wrong. If you know you've got a constant pressure process and it's not a horizontal line on your PV diagram, something's going wrong. If you know you've got an isentropic process and it's not a straight up and down line on this guy, something's gone wrong. And if you know you've got a constant temperature process and it's not a horizontal line on this, something's gone wrong. So the vertical and horizontal lines on this and the vertical and horizontal lines on this you should get always. The curvy lines are the ones that are a little bit harder to remember always. We know that T3 will be more than T2. And we know that V4 will be more than V1. I'm going to say that V is a constant and P is a constant, so that no matter whether or not I've remembered which way the curves go, it's clear that I knew what the process was supposed to be. So that's my way of cheating there. Or let's say it's a pro tip. 3, 4. So there's my PV diagram, my TS diagram for those things. And so what we're going to do now is with air assumptions. Now what hasn't been said here? What did we say in the previous question about the assumptions that hasn't been said here? What's the difference? So the answer down here was cold air assumptions as opposed to air assumptions. The other thing that the cold air assumption said was constant specific heats, assuming constant specific heats. Cold air assumption and constant specific heat enable you to use the Cp delta T and the Cv delta T. Air assumptions is what we were doing on Wednesday with those tables and the variable specific heats. The ideal air tables with the variable specific heats. Remember that Q23 is going to be, let's say little q23 is going to see Cp delta T, not Cv delta T, if I was using if constant, or is going to be delta H, not delta U, if variable C. Okay? Let's start to solve this. I'm going to redraw, just in the corner here, I'm going to redraw my PV diagram for the sake of 1, 2, 3, 4, for the sake of remembering where P and V are and where 1 and 2 and 3 and 4 are. Work around the cycle, finding U and H and maybe T. Okay, so once again we've got an adiabatic isentropic compression process is our first one. Yep. the reason I'm pausing is my solution that I've loaded up. My solution that I've loaded up the constant. So that's what I'm going to, because the numbers on the page I'm about to transfer to you and the ones that are uploaded are for constant specific heats, that's the one I'm going to solve for you. I'm more than happy to solve this with variable specific heats if you would like me to in the future. So process 1 to 2. Adiabatic isentropic. We've got T2 on T1 equals V1 on V2 to the gamma minus 1. So T2 equals T1 RV gamma minus 1. And we can put all those in, and we're going to get 873 Kelvin. And I'd like to have pressure here. I'd like to have pressure because it's a constant pressure process from 2 to 3, and so it may help me a lot to be able to get from 2 to 3 in terms of pressure. So this is equal to V1 on V2 to the gamma. If you've already looked at the equation sheets that get handed out, I give you these guys. So don't freak out about trying to remember them. It's nice if you can remember them, it saves you a lot of time. But knowing which one to use when is important. So P2 equals 101.3 times 13 to the 1.4 equals 3673 kilopascals. Process 2 to 3 is a constant pressure heat addition, and it's an ideal gas, which means I can use PV equals RT. So what I've got is that P3 V3 T3 equals P2 V2 T2, which is to say that PV equals RT, I can do PV on T equals R equals a constant. So I can say that PV on T equals PV on T. I can cross out my pressures because it's a constant pressure process. So V ratio gives me T ratio. That's why we give the cutoff ratio. Once I know the pressure at 2, if I use the cutoff ratio, which is to say the ratio of the volumes during the heat addition, I can give you the temperatures. So I've got the temperature at 2 already. I've got V2, I've got the ratio of V2 and V3. I can solve for T3. So what I get is T3 equals T2 V3 on V2, which is to say I've got 873 times 2 equals 1746 Kelvin. Now that's one of my answers. I was asked for what's the temperature at the hottest point in the cycle, and so the answer there is T3 is 1746 Kelvin, which is around about the temperature of a decent flame. That's good. That means we're on track. Now, process 3 to 4 is an adiabatic expansion. And so what I've got there is T4 on T3. Now here is going to come a trick. Equals V3 on V4 gamma minus 1. I've got RV. So for you guys looking at the graph, this way up, that's why I drew it. I've got RV from 1 to 2. I've got the volume from 2 to 3, but I want to solve this with a volume from 3 to 4. What happens is we work backwards. If I know the volume ratio from here to here and from here to here, I should be able to back calculate to work out what's the volume ratio from 3 to 4. So I'm going to do that over here. If RV equals V1 on V2 and RC equals V3 on V2 and V1 equals V4 by definition of the cycle, if I want V3 on V4, if V1 equals V4, that's the same as saying that this guy is V4 and V2. You with me there? Yep. So, what I'd like to have then is I want V3 on V2 times, what do I cancel out with? V2 on V4. If I can cancel my 2's here, I'll get this number, which is to say C on V. That magic trick is worth knowing if you're going to solve a diesel cycle. When I say something's worth knowing, I mean make sure you know this before Friday. People who were not in the lecture theatre didn't see me nodding and smiling just then. All right, which means now I've got this ratio, I can put that in. So I can say that T4 equals T3 times RC on RV gamma minus 1. Oops, off the screen. Equals 1746 times 2 on 13 to the 0.4 equals 825.8 Kelvin. Okay. Now, if I wanted to do the thermal efficiency by net work or net heat transfer, I find on these cycles the easiest way to do that is to do it with a net heat transfer. And this guy, we said before, we've got Cp T3 minus T2 minus Cv T4 minus T1 all over Cp T3 minus T2. And we'll just double check. I was given that temperature, I determined that temperature isentropically, I determined that temperature by constant pressure, and then I used all the various geometries to work my way around to this temperature. So I've got all the temperatures I need. I've got 1 and 4 and 2 and 3 and 2 and 3, and I've got CPs and I've got CVs. This can be solved for 58 to equal 58%. If you're curious, put the RC and RV values into the efficiency formula and confirm for yourself that the efficiency formula also works. We okay on this? Make sure you can get from 3 to 4, make sure on the diesel cycle you can get from 2 to 3, and you can get from 3 to 4. A mixed cycle. So the next example is a mixed cycle. This is a combo of Otto and diesel cycles. I think this question exists in the tutorial set. First you use a spark ignition to go up in pressure at constant volume, and then you use constant pressure process for the remainder of the heat addition. So we have a little bit of both. We define the cycle with the start of compression being 80 degrees and 1 atmosphere again, compression ratio 16 to 1, maximum cycle pressure of 80 atmospheres, and then if I'm using air, find the temperature at the end of the, if I'm using air and the temperature at the end of the expansion, the temperature at the end of the isentropic expansion is 500 degrees. So that's on my way back. So as you were looking at the graph, on my way back down to the exhaust process, work out the thermal efficiency and the mean effective pressure. Mean effective pressure is going to be net work over delta V, which means I'm going to need to determine my net work. Anytime I need to work out net work, I need to work out basically my temperatures all the way around this process. So let's draw the process, get the question started. At the moment, you're looking at it going, what does this even look like? It looks like a combo. So let's draw the graph before we do anything so that we've got it all mapped out nicely. P, V, axes. We said that we've got a constant pressure, a constant volume, and a constant pressure heat addition. So I've got Q in and Q in. I've got my normal isentropic compression, my normal isentropic expansion, and 1, 2, 3, 4, 5, Q out, work out, work in. So, given P1 equals 0.1 megapascals, T1 equals 80 degrees C equals 353 Kelvin. Given RV equals 16 to 1, or let's just say equals 16. Given P max equals P3 equals P4 equals 8 megapascals, and the T5 equals 500 degrees C equals 773 Kelvin, find MEP, which equals network. Remember, network is also Q in minus Q out, delta V. If this were done on a specific basis, this would be little w net and delta specific volume. So I don't necessarily need to know the actual volume change. And this, which is equal to W net on Q in. Now let's go around the cycle. Here, I'm just going to sketch the graph again so we keep track during this working. 1, 2, 3, 4, 5. P, V. Let's go. Process. By now, this mapping of the process should start to look familiar. 1 to 2, isentropic. So T2 on T1 equals V1 on V2, gamma minus 1. So T2 equals T1 RV, which we've been given, 1.4 minus 1, equals 353 times 16 to the 0.4 equals 1070 Kelvin. P2 on P1, remember, I don't have pressure 2. I've got pressure 3 and 4, but I don't have pressure 2. So this equals V1 on V2 to the gamma. So P2 equals P1 RV to the 1.4 is going to equal 4.85 megapascals. This has given me a lot of information already. Process 2 to 3 is constant volume and ideal gas. So I've got a PV equals RT thing going on here. So let's go P3, V3, T3 equals P2, V2, T2. And I've got this guy, this guy, this guy, this guy, this guy. This is a constant volume process. I've just determined P2. I've been given P3 in the equation, in the question, and so then I can solve this for T3 equals P3 on P2 times T2, which if I put it all in, I'm going to get 1764.8 Kelvin. I'm not trying to put in infinite decimal places, and decimal places imply a certain precision. I don't want to go too far in my decimal places. Now, at this point, we get a little bit stuck. I've gone 2 to 3. I'd like to go from 3 to 4, but I haven't been given this RC, so I don't know the volume. It's a constant pressure process, but I don't know the volume ratio. It's an ideal gas process. If I had the volume ratio, I'd be sweet. So, what to do? I can go backwards. 5 to 1. Backwards. That's a constant volume process, and I've been given the temperature. That's nice. So, with this, from 5 to 1, I can go V5 on T5. Is that still on the page? Nope. Equals P1 T1 on V1. So, P5, if I substitute in for all of those, remember, Vt. Remember, we've got this, it's a constant volume process, and we've got this, so P5 is going to equal 0.2189 megapascals if I substitute all that in. And so what? Well, the so what that I've got is that now, let's take a look at this process. If I've got pressure here, and I've got the pressure here, and it's isentropic, that's all I need to find my temperature. I've got a ratio of pressures, so I can find the ratio of temperatures. So what I've got then is 4 to 5 is isentropic. And now I'm still going backwards. Let's say T4 on T5 equals P4 on P5, gamma minus 1 on gamma. So T4 equals T5 of 8 on 0.2189 to the 0.4 on 1.4 equals 2161 Kelvin. And then, with all of that in place, let's see if I can get through this. I can get through this. Yes, we can. I've now got temperatures. Let's get this little sketch up again. My sketches are getting a little bit scarier every time I do them. 3, 4, 5. I've got the temperature here, 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 and here, which means that I can work out any Q's and W's and whatever I need to. So what I want to do is get net work, which is equal to Q in minus Q out, because I'm solving for the MEP. I look back at my question. By this time, I look back at what I wrote at the very top of the page. What was I trying to solve for? Trying to solve for MEP, which is net work over delta V. So I'm going to, Q, let's get rid of the mass on the screen. That's on the screen, which is CV T3 minus T2 plus CP T4 minus T3. That's Q in minus CV T5 minus T1. That's Q out. Internal energy for the constant volume process, enthalpy for the constant pressure process. If I plug all of those in, and I'm not going to write all the numbers down right now, I get 499 plus 397 minus 301.56. I get 595.44 kilojoules per kilogram, and MEP needs delta V or delta V. Whichever way I want to look at it, I can get my delta V with my ideal gas law, which is R T1 on P1 minus T2 on P2. Is that still on the screen? So this is using ideal gas law. So I'm sitting there going, how on earth do I get specific volume? Do I need to calculate it? Yes, I need to calculate it. I've got PV equals RT, and I've got my P's and T's all over the place, so I should be able to get my V's. So that's what happened there. And if I put all of those in to this great big MEP equals network over this, R T1 on P1 minus T2 on P2. I should be able to solve this for 626.8 kilopascals and an efficiency of work net over Q in. I've already worked out Q in up here. And so then I can get 595.44 over 499 plus 397. This is Q in. Is going to equal 66.4%. So that was flat out. We're almost done for time. But it was 3 questions in an hour, including some preamble, waffle, and motivational conversation. I'm happy to go through those, any of the concepts from them. If you send me photos from the working, if I just took the page down and you were in the middle of writing something down, all the notes are written in much neater handwriting on the LMS.
Yeah.